Once upon a time, in the ancient world of mathematics, there existed a vast and uncharted territory known as geometry. Among its many landscapes, the circle stood as one of the most fundamental and fascinating figures. Scholars from different civilizations pondered over its properties, striving to understand its mysteries. In ancient Greece, around the 5th century BCE, the mathematician Hippocrates of Chios began to explore the properties of circles. He discovered that the ratio of the circumference to the diameter of any circle was a constant, which we now know as pi. This discovery laid the groundwork for understanding circles. But the journey was far from over. Centuries later, another great Greek mathematician, Euclid, took the stage. In his monumental work, Elements, Euclid defined the circle and described many of its properties. However, the concept of the unit circle, a circle with a radius of 1 unit, had yet to emerge. The development of trigonometry in the Hellenistic period brought new insights. Hipparchus of Nicaea, known as the father of trigonometry, created the first known trigonometric tables. These tables helped astronomers and mathematicians relate angles to the lengths of chords in a circle. Yet, the specific notion of a unit circle still eluded them. Fast forward to the Islamic Golden Age, where scholars like Al-Khwarizmi and Al-Battani made significant contributions to mathematics and astronomy. They translated and built upon Greek works, including those on trigonometry. Their efforts brought the mathematical community closer to a more refined understanding of circles and angles. It was during the Renaissance, with the revival of classical knowledge and the dawn of new ideas, that the concept of the unit circle truly began to take shape. Mathematicians such as Regiomontanus and Copernicus explored trigonometric functions more deeply, recognizing the importance of standardizing the radius of the circle to 1 unit for simplicity and consistency. In the 17th century, the unit circle finally solidified its place in mathematics. The French mathematician François Vite and his successors used the unit circle to define trigonometric functions. They understood that by fixing the radius at 1 unit, the sine, cosine, and tangent of an angle could be directly related to the coordinates of points on the circle. The unit circle became a powerful tool for solving problems in trigonometry, allowing for the visualization of angles and the relationships between different trigonometric functions. It provided a geometric interpretation that was both intuitive and elegant. As the centuries passed, the unit circle found applications in various fields, from physics to engineering, and even in the emerging field of complex numbers. It became a cornerstone of mathematical education, a simple yet profound concept that continues to inspire and enlighten students and scholars alike. And so, the story of the unit circle is a testament to the collaborative and cumulative nature of mathematical discovery. From the ancient Greeks to the Renaissance thinkers, and beyond, the development of the unit circle exemplifies the timeless quest for knowledge and understanding that defines the spirit of mathematics. The story of the unit circle is enriched by contributions from scholars across the world, including significant advancements from India during the classical period. Indian mathematicians and astronomers made remarkable strides in trigonometry, which laid the groundwork for the concept of the unit circle and trigonometric functions. Around the 5th century CE, the renowned Indian mathematician and astronomer Aryabhata made significant contributions to trigonometry. In his seminal work, the Aryabhatiya, Aryabhata introduced the sine function, jaya, and produced tables of sine values for various angles. His work marked a departure from the Greek approach of using chords, instead focusing on the half-chord, which we now call the sine function. Aryabhata's sine table was accurate and provided a foundation for later advancements in trigonometry. Building on Aryabhata's work, another prominent Indian mathematician, Varahamihira, also contributed to the development of trigonometry in the 6th century CE. In his encyclopedic work, the Brihat Samhita, Varahamihira provided further trigonometric calculations and applications, demonstrating the practical utility of these concepts in fields like astronomy and astrology. The tradition of mathematical excellence continued with the work of Bhaskara I in the 7th century CE. Bhaskara I provided detailed explanations and improvements on Aryabhata's sine tables, further refining trigonometric calculations. He also introduced the concept of the versine, versin equals 1 minus cos, which played a role in the development of trigonometric identities and relationships. One of the most significant contributions came from the 12th century mathematician Bhaskara II, also known as Bhaskarakarya. In his monumental work, the Siddhanta Shromani, Bhaskara II presented comprehensive treatments of trigonometric functions, including sine, cosine, and their inverses. His work on these functions and their relationships can be seen as precursors to the modern understanding of the unit circle and its role in trigonometry. The Indian scholar's method of relating trigonometric functions to the circle influenced the later development of the unit circle concept. By focusing on the half-chord, sine, and its properties, they provided a framework that made it easier for later mathematicians to visualize and standardize trigonometric functions on a circle with a fixed radius of 1 unit. In summary, the contributions from Indian mathematicians like Aryabhata, Varahamihira, Bhaskara I, and Bhaskara II played a crucial role in advancing trigonometry. Their work laid the foundational principles that would later integrate into the broader concept of the unit circle, illustrating the interconnected and global nature of mathematical progress. Once upon a time, in the heart of the modern mathematical kingdom, the unit circle stood as a powerful and unifying symbol. Its origins were ancient, rooted in the works of the great scholars of Greece and India, but its influence had grown immensely in the contemporary world. The story of the unit circle in modern times begins with a group of curious students in a bustling classroom. Their teacher, Ms. Harper, stood before them with a smile, ready to unveil the secrets of the circle. "Today, we'll explore the magic of the unit circle," she announced, her eyes sparkling with excitement. With a wave of her hand, Ms. Harper drew a perfect circle on the board, its center at the origin of a coordinate plane, and its radius precisely 1 unit long. "This," she said, "is our unit circle. It may seem simple, but it's a gateway to understanding so much of the world around us." She began by explaining how the unit circle helps define trigonometric functions. Imagine an angle theta, measured from the positive x-axis. As we move around the circle, the coordinates of our point are cos, sin. These are our beloved cosine and sine functions, which help us understand waves, oscillations, and even the rhythms of music. The students were captivated, but Ms. Harper was just getting started. She ventured into the realm of complex numbers, where the unit circle revealed even deeper mysteries. "In the complex plane," she said, "every point on the unit circle represents a complex number of the form cos plus sin. This is Euler's formula, and it's the cornerstone of so many mathematical theories." Ms. Harper illustrated how Euler's formula linked trigonometry to the exponential function, showing how it could describe everything from the swinging of a pendulum to the quantum states of particles. The students marveled at how a simple circle could be so profound. Next, she took them on a journey into the world of Fourier transforms. "Here," she said, "the unit circle helps us break down complex signals into simple periodic components. This is the magic behind digital music, image processing, and even the way we compress videos." The students imagined the world of signals and frequencies, understanding that every sound they heard and every image they saw could be analyzed using the unit circle. The circle's power seemed limitless, but Ms. Harper wasn't finished. She revealed how the unit circle played a key role in computer graphics. When we create animations or render 3D objects, we use the unit circle to calculate rotations and transformations. It's what makes our favorite video games and movies come to life. The students envisioned the heroes and worlds of their beloved games, all brought to existence through the mathematical prowess of the unit circle. As the lesson drew to a close, Ms. Harper shared one more secret. "In machine learning and data science," she said, "the unit circle helps us understand the patterns and relationships in complex data. It's a tool that guides us in making sense of the vast amounts of information in our digital age." The students sat in awe, realizing that the unit circle was not just a geometric shape, but a bridge connecting countless domains of knowledge. It was a testament to the unity of mathematics, science, and technology, all woven together by this simple, elegant figure. And so, in the modern world, the unit circle continued to inspire and enlighten, a timeless symbol of the interconnectedness of all things mathematical. Its story, ever evolving, was a reminder of the endless wonders that lay hidden in the world of numbers, waiting to be discovered by curious minds. Welcome everyone to our presentation on the Riemann hypothesis. Today, we will explore some of the most fascinating aspects of number theory and delve into one of its most enduring mysteries, Euler's initial work. We begin with the remarkable contributions of Leonhard Euler. In the 18th century, Euler made groundbreaking discoveries in understanding infinite series. He introduced the idea that the harmonic series, which is the sum of the reciprocals of the positive integers, could be expressed as a product over prime numbers. This was a revolutionary insight, as it linked the seemingly simple harmonic series to the complex and profound properties of prime numbers. Euler's formula was one of the first indications of the deep connections between primes and series. Basel problem solution. Euler didn't stop there. He also tackled the Basel problem, which was concerned with finding the exact sum of the reciprocals of the squares of the integers. By examining the sine function and its product representation, Euler derived a formula for this sum. He showed that the sum of these reciprocals is equal to pi caret 2/6. This result was a significant achievement in mathematics and highlighted Euler's ability to uncover connections between different mathematical concepts. Riemann's analytical machinery. Moving to the 19th century, we encounter Bernhard Riemann, who expanded our understanding of complex functions. Riemann introduced the concept of analytical continuation, which allowed for the extension of functions beyond their initial domains. For example, he extended the Riemann zeta function, which was initially defined only for complex numbers with real parts greater than 1, to the entire complex plane except for s equals 1, where it has a simple pole. This was a crucial advancement in complex analysis and paved the way for deeper exploration of functions. Riemann's zeta function. The Riemann zeta function is central to our discussion. For values of s with real parts greater than 1, it is defined as the sum of the reciprocals of integer powers. Riemann's extension of this function to all complex numbers, except s equals 1, revealed new dimensions of mathematical exploration. The zeta function became a key object of study in number theory and complex analysis, connecting various areas of mathematics. Dirichlet eta function. Riemann was also influenced by the Dirichlet eta function, defined by an alternating series. This function is closely related to the zeta function and provides valuable insights into its behavior, particularly for values of s less than 1. The relationship between the eta function and the zeta function is encapsulated in a simple formula involving the gamma function and powers of 2, which helps in understanding the zeta function's properties across different regions. Reflection properties. One of Riemann's major discoveries was the reflection formula for the zeta function. This formula demonstrates a symmetry between the values of the zeta function at s and 1 minus s. Specifically, it shows that zeta 1 minus s can be expressed in terms of zetas using factors involving pi, the gamma function, and trigonometric functions. This reflection formula is fundamental to the theory of the zeta function and provides deep insights into its structure. Jacobi theta function. Riemann also made use of the Jacobi theta function, which has significant applications in various areas of mathematics. The theta function's series representation and modular properties were instrumental in Riemann's derivation of the functional equation for the zeta function. This equation is crucial for understanding the zeta function's behavior across the complex plane and highlights its intricate connections to other mathematical functions. Functional equation of the zeta function. The functional equation of the zeta function relates its values at s and 1 minus s through a complex expression involving pi, the gamma function, and trigonometric functions. This equation is a key result in the theory of the zeta function, showcasing its symmetry and the deep relationships between different mathematical concepts. Riemann's seminal paper. In 1859, Riemann published his seminal paper on the distribution of prime numbers, which introduced the zeta function and laid the groundwork for modern analytic number theory. This paper was a milestone in mathematical history and has had a lasting impact on the field, influencing subsequent research and discoveries. Riemann's hypothesis. Finally, we address the Riemann hypothesis itself. Riemann proposed that all non-trivial zeros of the zeta function lie on the critical line where the real part of s is half. This hypothesis has profound implications for number theory, particularly in understanding the distribution of prime numbers. Despite extensive numerical evidence supporting the hypothesis, a formal proof or disproof remains one of the greatest challenges in mathematics. The story of Riemann hypothesis continues. In a bustling town, Kolkata in India, there lived an accountant named Suraj. By day, he meticulously balanced books and ensured that every penny was accounted for. His life an intricate dance of numbers. But by night, Suraj's world transformed into something far more extraordinary. One day, while poring over some physics concepts, Suraj stumbled upon a reference to the dimensionless fine structure constant. This constant, a fundamental number in physics, had always intrigued him with its mysterious significance. As he delved deeper into its properties, another thought surfaced in his mind, a thought that linked this constant to something called Charles's constant, which he had encountered during one of his late-night reading sessions. Charles's constant was nearly half the value of the fine structure constant, and this curious relationship set Suraj's mind racing. Could there be a connection between these two constants? And if so, was it purely coincidental? Or was there a deeper mathematical truth hidden beneath the surface? As an accountant, Suraj was accustomed to finding patterns and relationships in numbers, especially when it came to averages. He thought about the various averaging methods he used in his work, calculating the average inventory, average receivables, and average payables. These techniques, though simple, often revealed trends and insights that were not immediately apparent in the raw data. Could the relationship between the fine structure constant and Charles's constant be similar? Could it be the result of some form of averaging, akin to the techniques used in accounting? The idea intrigued Suraj, and he couldn't shake the feeling that there was something more to this connection. With renewed energy, Suraj began to explore this possibility, applying the principles of algebra and intuition that had guided him so far. He knew that if there was indeed a link between these constants, it could be a crucial piece of the puzzle in his quest to understand the Riemann hypothesis. As he worked through the numbers, Suraj felt a familiar excitement building within him. This was the thrill of discovery, the joy of uncovering something new and unexpected. And though he was still far from his ultimate goal, Suraj knew that every step he took brought him closer to unraveling the mysteries of the universe, one equation at a time. Another day, as Suraj was browsing through a Wikipedia page on the list of unsolved problems in physics, something intriguing caught his eye, a link to unsolved problems in mathematics. Feeling curious, he clicked on it and began to scroll through the list, wondering what mathematical mysteries awaited him. As he scanned the page, a statement suddenly made him stop in his tracks. There it was, the Riemann hypothesis. Suraj had never heard of it before, but something about the problem drew him in. The hypothesis stated that the non-trivial zeros of the Riemann zeta function all had a real part of 1/2. This was the first time Suraj had encountered this problem, and he couldn't help but feel a strange sense of familiarity with the concept of half. In his accounting work, half was a number he knew well, whether it was dividing assets, calculating averages, or finding midpoints. But here, in this grand, unsolved problem of mathematics, it seemed to take on a new, almost mystical significance. Suraj pondered this idea. Could there be a connection between the simple notion of half that governed so much of his daily life and this profound mathematical problem? The idea seemed far-fetched, yet it also felt oddly intuitive. The more he thought about it, the more he was convinced that there was something here, something worth exploring. This moment marked a turning point for Suraj. The Riemann hypothesis had captured his imagination, and he couldn't resist the urge to delve deeper. He didn't fully understand the problem yet, but he knew that his journey into this world of numbers had only just begun. And as he sat back, staring at the screen, Suraj realized that this was the beginning of a new chapter in his life, one where his love for numbers might just lead him to uncovering one of the greatest mysteries of all. Suraj's journey into the world of the Riemann hypothesis led him to the works of one of mathematics' greatest pioneers, Leonhard Euler. Eager to understand the roots of the problem, Suraj started with Euler's exploration of the zeta function, which had laid the groundwork for so much of modern mathematics. He delved into the Basel problem, a famous puzzle that had baffled mathematicians for decades until Euler solved it with his remarkable ingenuity. Euler had shown that the sum of the reciprocals of the squares of the natural numbers was equal to pi squared divided by 6. This elegant solution amazed Suraj not just for its precision, but for how it connected an infinite series to a fundamental constant, pi. As Suraj continued to explore Euler's contributions, he discovered even more about this mathematical giant. He learned about Euler's identity, often referred to as the queen or jewel of mathematics, which elegantly unified the trigonometric and complex exponential unit circles. The identity encapsulated 5 of the most important constants in mathematics, e, I, pi, 1, and 0, into a single simple equation. Suraj was captivated by the beauty of this identity. The way it tied together seemingly disparate areas of mathematics resonated deeply with him, especially the idea of unification. In his mind, this unification was not unlike the balance and harmony he sought in his own work as an accountant. With each discovery, Suraj's fascination with the Riemann hypothesis grew. He began to see the problem not just as a daunting mathematical challenge, but as part of a larger tapestry woven through the history of mathematics, connecting the work of great minds like Euler. This newfound understanding inspired Suraj, fueling his determination to explore the hypothesis further and to seek out the hidden connections that might lead him to its solution. As Suraj delved deeper into Euler's work, he discovered a fascinating mathematical technique, Euler's trick of converting sums into products. This method, which connected the additive and multiplicative structures of numbers, intrigued Suraj. It was a simple yet profound insight that had allowed Euler to explore the properties of the zeta function in new and unexpected ways. Inspired by this idea, Suraj decided to take it one step further. He set out to calculate the infinite product of zeta values both from the sum side and the product side using an induction approach. His goal was to see if this method would reveal any new insights into the behavior of the zeta function, particularly around its critical points. As he worked through the calculations, Suraj arrived at a surprising result. According to his method, the value of the zeta function at s equals 1 seemed to equal 1. This caught him off guard because he knew that zeta 1 was known to be divergent, a fact first established by Nicole Oersma through his comparison test, and later confirmed by Riemann's functional equation which showed a pole at s equals 1. This unexpected result presented Suraj with a new challenge. How could he reconcile his findings with the well-established knowledge that zeta 1 was divergent? He realized that the answer might lie in the concepts of regularization or renormalization, mathematical techniques used to make sense of infinite or undefined quantities. The idea of dealing with essential singularities fascinated Suraj. These were points where a function behaved in a wildly unpredictable manner, and yet there was a possibility of taming this behavior through careful mathematical manipulation. Suraj saw this as a clue, a potential key to unlocking a deeper understanding of the Riemann hypothesis. Driven by this new insight, Suraj immersed himself in the study of regularization and renormalization techniques. He knew that this was uncharted territory for him, but he was determined to explore it. After all, he had already come so far by trusting his intuition and applying simple, yet powerful mathematical principles. This was just the next step in his extraordinary journey. Suraj knew that tackling renormalization was a daunting task, especially for someone with his background. He decided to take a step back and focus on something more manageable, something that still held the potential to reveal new insights. With his newfound understanding of Euler's methods, Suraj began to experiment. He injected the exponential form of complex numbers into Euler's sum-to-product form, a technique that intrigued him because of its elegant connection between different areas of mathematics. As he worked through the equations, Suraj found himself landing on a familiar and fundamental concept: the unit circle. The unit circle, with its perfect symmetry and balanced rotation, was a powerful visual representation of mathematical principles. Suraj realized that on this circle, the principle of symmetry was obeyed through rotation, with each step around the circle reflecting an additive identity. This discovery excited Suraj. He knew that symmetry was a fundamental aspect of mathematics, often hinting at deeper underlying structures. If he was right, then there must be more structural symmetries waiting to be uncovered, patterns that could potentially lead him closer to solving the Riemann hypothesis. Suraj's intuition told him that these symmetries were not just mathematical curiosities. They were essential clues, guiding him toward a deeper understanding of the zeta function and its mysterious zeros. With this in mind, he set out to explore the unit circle further, searching for hidden connections and patterns that could unlock the next piece of the puzzle. As he continued his work, Suraj felt a growing sense of anticipation. He was no longer just an accountant dabbling in mathematics. He was a seeker, on the verge of discovering something profound. The journey was far from over, but Suraj knew that he was on the right path, guided by the simple beauty of symmetry and the elegant dance of numbers. Suraj's intuitive search for symmetries led him to delve deeper into the mathematics that had always fascinated him. He began experimenting with basic algebra, using known values of the zeta function, including the intriguing result from Ramanujan that zeta minus 1 equals minus 1 upon 12. This value, though counterintuitive, hinted at the rich and complex nature of the zeta function and its connection to the deeper structure of mathematics. As Suraj manipulated these values and explored symmetrical patterns around zero, he found himself drawn to familiar trigonometric identities. He noticed that his calculations began to converge on specific angles, particularly those involving pi/3 or pi/6. These angles were special as they both equaled either square root 3 over 2 or half, a value that resonated with the geometric and algebraic symmetries he had been exploring. To his surprise, Suraj realized that these trigonometric values were not just coincidental. They seemed to be connected to the zeros of the zeta function in a subtle yet profound way. The symmetry he had been searching for was beginning to reveal itself, weaving together the threads of algebra, trigonometry, and the complex structure of the zeta function. This discovery thrilled Suraj. He felt that he was on the verge of uncovering a hidden connection, one that could bridge the gap between the simplicity of high school mathematics and the deep complexities of the Riemann hypothesis. With renewed determination, Suraj continued his exploration, eager to see where this path of symmetry and intuition would lead him next. Suraj's journey had led him to a profound realization. He had found a compelling reason why the Riemann hypothesis must be true. The symmetries and patterns he had discovered, combined with his understanding of basic algebra and trigonometry, had convinced him that the zeros of the zeta function were indeed aligned in the way the hypothesis predicted. But finding the reason was just the beginning. Suraj knew that to truly prove the Riemann hypothesis, he needed to move beyond intuition and provide a rigorous mathematical proof. The next big task ahead of him was to address the poles of the zeta function, which posed a significant challenge. As he studied the problem, Suraj observed that the poles of the zeta function could not be renormalized without first dealing with the poles of the gamma function. The gamma function, closely tied to the zeta function through the functional equation, had its own set of poles, and these needed to be carefully managed if he was to remove the singularities in the zeta function. This realization brought Suraj to a critical juncture. He knew that the task ahead would require meticulous work and a deep understanding of both functions. The poles, representing points where the functions blew up to infinity, were like obstacles blocking his path. To clear the way, Suraj would need to find a method to cancel or regularize these poles, making the zeta function well-behaved across the complex plane. With this new challenge before him, Suraj felt a mix of excitement and determination. He knew that he was venturing into complex and uncharted territory, but he also knew that this was the crucial step needed to solidify his proof. The journey had been long and filled with unexpected discoveries, but Suraj was ready to take on the final task and see his work through to completion. As Suraj delved deeper into the mathematics of the zeta and gamma functions, he encountered another intriguing issue. He realized that factorial functions, fundamental to many areas of mathematics, had no inverse, a fact that seemed to challenge the symmetrical principles of multiplicative identity. Factorials, which grow rapidly with each positive integer, did not have a straightforward inverse function. This was particularly problematic when extending the concept to complex numbers, as there was no functional representation for negative factorials. This absence of an inverse seemed to contradict the symmetric laws that underpinned much of algebra and arithmetic. Moreover, Suraj discovered that factorials were not closed algebraically under complex numbers. Higher analogues of factorials, such as the gamma function, also faced limitations. The gamma function, though a generalization of the factorial function to complex numbers, still did not resolve the issue of negative factorials, nor did it provide a complete algebraic closure. This realization added another layer of complexity to Suraj's task. The lack of closure and the absence of inverses for factorials indicated that there were fundamental gaps in the algebraic structure he was working with. These gaps needed to be addressed to achieve a comprehensive proof of the Riemann hypothesis. Suraj knew that resolving these issues would require innovative thinking and a deep dive into advanced mathematical theories. Yet, despite the challenges, he remained undeterred. His journey had already taken him through unexpected discoveries and profound insights, and he was determined to navigate these new complexities as well. With every challenge, Suraj grew more resolute in his quest to unlock the mysteries of the Riemann hypothesis and complete his proof. To tackle the challenge of the factorial functions and their limitations, Suraj decided to innovate. He took inspiration from Euler's gamma function and created a new variant by shifting its argument down by 1 unit. This adjustment provided an additional depth, effectively removing the problematic pole at 0. This new function, which Suraj named the capital delta function due to its triangular appearance, proved to be self-recursive. It maintained a consistent 1-unit distance from the gamma function, providing a useful modification to handle the issues he had encountered. Suraj was careful to distinguish his capital delta function from other delta functions in use, such as Dirac's delta function, which had a different role and properties. His capital delta function was designed specifically to address the challenges of the gamma function and its limitations. With this new tool at his disposal, Suraj felt more equipped to tackle the complexities of his proof. The capital delta function offered a fresh perspective and a potential solution to the problems he faced. As he continued his work, Suraj hoped that this innovative approach would bring him closer to a rigorous proof of the Riemann hypothesis, bridging the gaps he had discovered and adding a new dimension to his mathematical journey. With the capital delta function ready, Suraj turned his attention to incorporating it into the Riemann zeta function's functional equation. This was a crucial step in addressing the poles and singularities that had previously posed challenges. The original functional equation for the zeta function involves several components. Suraj aimed to modify it by integrating his newly developed capital delta function. Here's how he approached it. 1. Incorporating the capital delta function. Suraj began by adapting the gamma function term in Riemann's equation. Instead of the gamma function, he introduced the capital delta function. The revised equation looked like this. The zeta function of s was now expressed in terms of the zeta function at 1 minus s, multiplied by other factors including the capital delta function. Specifically, the equation used the capital delta function to handle the singularities at 0. 2. Testing and verification. Suraj carefully tested this new equation across various values of s. He needed to ensure that the revised equation worked correctly and did not introduce any new issues. This involved comparing his results with known outcomes and verifying that the changes resolved the singularity problems. 3. Exploring implications. By integrating the capital delta function, Suraj hoped to simplify the zeta function's behavior, particularly around its poles. This adjustment aimed to provide a more stable foundation for his proof, helping to address some of the core challenges associated with the zeta function's singularities. This effort to rebuild the functional equation marked a significant step in Suraj's journey. It was a move towards resolving the complex issues he had encountered and advancing his work on the Riemann hypothesis. With this innovative approach, Suraj was hopeful that he was closer to achieving a breakthrough. The initial manipulation of incorporating the capital delta function into the Riemann zeta function's equation showed promise. However, deriving the complete alternate functional equation proved to be more challenging than Suraj anticipated. He faced several hurdles in ensuring that all components aligned correctly. To tackle these challenges, Suraj needed to 1. Exploit gamma function's reflection. The gamma function's reflection formula is a critical tool in complex analysis. Suraj used this formula to help manage the singularities and poles. This reflection property relates the gamma function evaluated at s and 1 minus s, providing valuable insights into its behavior across different regions of the complex plane. 2. Utilize zeta function's reflection. Similarly, the reflection properties of the zeta function were crucial. Suraj needed to carefully apply these properties to ensure that the alternate functional equation maintained consistency and accuracy. 3. Handle zeta function's limit. The behavior of the zeta function at various limits was another key consideration. Suraj had to ensure that the new equation correctly accounted for the zeta function's behavior as s approached specific values, particularly those where it exhibited known divergences or special properties. 4. Apply various translations and transformations. Suraj explored different translations and transformations to align the new functional equation with the known properties of the zeta function. These transformations helped manage the relationship between the zeta function and the capital delta function, ensuring that the new equation was both consistent and effective. Suraj's approach involved meticulous calculations and a deep understanding of complex function theory. Despite the challenges, he was determined to refine the equation step by step. Each adjustment brought him closer to a robust solution that could potentially resolve the singularity issues and support his proof of the Riemann hypothesis. As he worked through these complexities, Suraj's perseverance and mathematical intuition guided him. He remained hopeful that his efforts would lead to a significant breakthrough in his quest to solve one of mathematics' most profound problems. After much effort, Suraj had successfully derived the alternate functional equation for the Riemann zeta function, incorporating his capital delta function. The next crucial step was to test this new equation to see if it supported the proof of the Riemann hypothesis. To test the alternate functional equation, Suraj chose a specific value to evaluate it. He set the left-hand side of the equation to the zeta function evaluated at half. This choice was strategic, as evaluating the function at this point could reveal if the right-hand side of the equation approached zero in a generalized manner. Here's what Suraj did. 1. Setting the test value, Suraj substituted half into the left-hand side of the alternate functional equation. This choice was significant because the behavior of the zeta function at this point was of particular interest and could provide insights into the nature of its zeros. 2. Evaluating the right-hand side. By evaluating the right-hand side of the equation with the same test value, Suraj aimed to determine if it approached zero. If the right-hand side consistently approached zero when the left-hand side was set to half, it would suggest that the equation might indeed support the existence of zeros at specific points. 3. Interpreting the results. The results of this test were crucial. If Suraj found that the right-hand side went to zero in a generalized way, it would provide strong evidence that the alternate functional equation was correctly structured and that the zeta function had the desired properties. Suraj's careful testing was a significant step toward confirming the validity of his new approach. If successful, this test could bring him closer to demonstrating that the Riemann hypothesis holds true under his revised framework. With each step forward, Suraj felt a growing sense of excitement and anticipation, knowing that he was inching closer to solving one of the greatest mathematical puzzles. Suraj's test was a success. When he set the left-hand side of the alternate functional equation to the zeta function evaluated at half, he found that the right-hand side approached zero in a generalized manner. This was a significant breakthrough. The successful test meant that the alternate functional equation, incorporating the capital delta function, was behaving as hoped. It supported the idea that the zeta function could be aligned with the hypothesis about its zeros. This result validated Suraj's approach and provided a crucial piece of evidence for his proof. With this success, Suraj felt a renewed sense of accomplishment and motivation. His innovative use of the capital delta function and the careful derivation of the alternate functional equation had paid off. He was now closer than ever to proving the Riemann hypothesis. This milestone was a testament to Suraj's dedication, creativity, and deep understanding of mathematics. As he prepared to finalize his proof, he knew that the journey was not yet over, but this achievement was a major step toward completing one of the most challenging problems in mathematics. With the successful validation of his alternate functional equation, Suraj moved on to the next critical phase of his work: unification. This step involved integrating his findings into a cohesive framework that would solidify his proof of the Riemann hypothesis. Here's how Suraj approached the unification process. 1. Integrating the capital delta function. Suraj began by ensuring that the capital delta function was seamlessly incorporated into the overall framework of his proof. He needed to confirm that this new function worked harmoniously with the zeta function and did not introduce inconsistencies. 2. Aligning with existing theories. Suraj reviewed his results to ensure they aligned with established mathematical theories and principles. This included checking compatibility with known results and theories related to the zeta function, the gamma function, and other related functions. 3. Verifying consistency across equations. Suraj examined the consistency of his revised functional equation across various scenarios and values. He needed to ensure that the equation held true not just for specific cases, but in general, providing a robust foundation for the Riemann hypothesis. 4. Finalizing the proof. With everything in place, Suraj worked on consolidating his findings into a final proof. This involved clearly presenting his results, demonstrating how his approach resolved the key issues related to the Riemann hypothesis, and addressing any remaining concerns. 5. Ensuring rigorous validation. Suraj sought to validate his proof rigorously. He conducted thorough checks and possibly sought feedback from peers or experts to ensure that his proof was solid and free from errors. As Suraj approached the unification phase, he knew that this was a crucial step in completing his proof. Unifying his findings meant bringing together all the components of his work into a single, coherent argument. This final step would determine whether his approach could stand up to scrutiny and whether he could claim success in proving one of the most famous conjectures in mathematics. With determination and careful attention to detail, Suraj set out to complete this pivotal phase of his journey, hopeful that his proof would be a significant contribution to the field. Now over to Suraj for rest of the story. The quest for unification. At the heart of my proof lies the extension of the Riemann zeta function. The key was an alternate functional equation, one that emerged from the reflection properties inherent in both the zeta and gamma functions. This equation wasn't merely a mathematical curiosity. It became the linchpin of a deeper understanding. By weaving together this new variant of the zeta function with Euler's zeta function, I discovered a surprising harmony. These two distinct functions acted as harmonic conjugates, complementing each other in a dance of mathematical elegance. This union provided a unified framework, allowing the zeta function to transcend its previous limitations. The role of the dual unit circle. The unification led to a profound transformation of the zeta function. It evolved into an entire function, meaning it became holomorphic across the entire complex plane. But this transformation wasn't just about removing singularities. It reshaped the very nature of the zeta function's behavior. In this new form, the zeta function reaches its maximum modulus not within the traditional boundaries but beyond the unit circle, on what I describe as the boundary of the dual unit circle. This boundary became a critical region, revealing the peak of the function's amplitude. Conversely, the function's zeros, the elusive points that hold the key to the Riemann hypothesis, emerged on the half-unit circle where the modulus is minimized. Complying with Liouville's theorem. This behavior aligns seamlessly with Liouville's theorem. The theorem, a cornerstone of complex analysis, asserts that a bounded entire function must be constant. However, the newly unified zeta function, unbounded in its domain, navigates through the landscape of the dual unit circle, obeying the maximum modulus principle in a way that resonates with Liouville's insights. A new perspective on an ancient problem. This narrative represents not just a mathematical proof but a new perspective on an age-old problem. By extending the zeta function through alternate paths and finding harmony in its dual nature, we uncover a structure that aligns with the deepest principles of complex analysis. The Riemann hypothesis, long considered insurmountable, may now have a new avenue toward resolution. This journey is a testament to the power of unification and the beauty of finding connections where none were previously seen. The zeta function, once constrained, now stands as a testament to the boundless potential of mathematical exploration. In any groundbreaking work, especially one as monumental as a proposed proof of the Riemann hypothesis, critique and skepticism are inevitable. The strength of my proof lies not only in the mathematical rigor but in the innovative approach that challenges traditional boundaries. Embracing novelty in mathematics. Critics may argue that extending the Riemann zeta function through an alternate functional equation is unconventional. However, history has shown that mathematical progress often comes from reimagining established concepts. The alternate functional equation derived from the reflection properties of the zeta and gamma functions is not an arbitrary extension. It is deeply rooted in the inherent symmetries of these functions. By exploring these symmetries, I've uncovered a new perspective that adds coherence to the zeta function's behavior. Harmony with established theories. Some may question the unification of the zeta function with Euler's zeta function, seeing them as distinct entities. Yet, in complex analysis, the concept of harmonic conjugates is well established. By positioning these functions as harmonic conjugates, I've created a framework that unifies their behavior, offering a more comprehensive understanding of their relationship. This unification is not a departure from tradition but an expansion of it, extending the reach of what we know. Addressing the behavior on the dual unit circle. The introduction of the dual unit circle and the function's behavior on its boundary may be seen as speculative. However, this approach is firmly grounded in the principles of complex analysis. The concept of dual structures is not new. It's a natural extension of the geometric interpretations of complex functions. The maximum modulus principle, as applied to the boundary of the dual unit circle, is a logical extension of classical theorems, including Liouville's theorem. By demonstrating that the zeta function's zeros align with the minimum modulus on the half-unit circle, I've provided a concrete manifestation of this theoretical framework. Rigor and mathematical integrity. Critics might also focus on the need for absolute rigor. Every step of my proof has been carefully constructed, with a focus on mathematical integrity. The extensions and transformations I propose are not mere conjectures. They are supported by deep analysis and rooted in established mathematical theory. The new perspectives I introduce are not about bending the rules of mathematics but about applying them in innovative ways to reach new conclusions. The role of skepticism in advancing knowledge. I welcome skepticism as it is a vital part of the mathematical process. It ensures that ideas are tested, refined, and either validated or disproven. My work is open to scrutiny, and I encourage my peers to engage with it critically. If my proof withstands this scrutiny, it will only be stronger for it. If there are aspects that can be improved or refined, I am committed to addressing them, as my goal is the pursuit of truth, not the defense of an unassailable position. In defending my work, I stand by the innovative methods and rigorous analysis that have guided my proof. I believe that by embracing new perspectives and challenging traditional boundaries, we can move closer to resolving one of the most profound questions in mathematics. Critics may assert that any valid proof of the Riemann hypothesis must be derived exclusively from the classical Riemann zeta function itself, without involving variants or related functions. This view, while rooted in traditional approaches, overlooks the rich interplay between related mathematical objects and the potential of such relationships to unlock deeper insights. The power of harmonic conjugates. Harmonic conjugates are not mere mathematical conveniences. They represent a profound symmetry in complex analysis. By considering the Riemann zeta function in tandem with its harmonic conjugates, such as the alternate variant derived through the reflection properties of the zeta and gamma functions, we tap into a broader framework. This framework doesn't detract from the Riemann zeta function's centrality, but rather enriches it, offering new pathways to understand its properties. Historical precedents in mathematical discovery. History is replete with examples where significant breakthroughs were achieved not by direct attack on a problem, but by exploring related functions or objects. For example, the relationship between the sine and cosine functions, which are harmonic conjugates, is essential for understanding Fourier analysis. Similarly, the discovery of the analytic continuation and functional equation of the Riemann zeta function itself was a step away from its original definition, leading to deeper insights. Expanding the conceptual framework. The idea that a proof of the Riemann hypothesis must emerge strictly from the Riemann zeta function is based on a narrow view of mathematical exploration. In complex analysis, functions are often best understood in the context of their relationships with other functions. The use of variants as harmonic conjugates is not about sidestepping the problem but about expanding the conceptual framework within which the problem is considered. This expansion allows for a more comprehensive understanding, where the behavior of the zeta function can be seen in a new light. Unity in diversity, the zeta function and its variance. The assertion that only the Riemann zeta function should be used neglects the fact that variants of the zeta function, when considered as harmonic conjugates, still hold the essence of the original function. They are not separate entities but are intrinsically linked to the Riemann zeta function, sharing fundamental properties and behaviors. The unification of these functions brings to light a broader, yet coherent, picture of the zeta function's behavior across different domains. The role of generalization in proofs. In many areas of mathematics, generalization plays a crucial role in finding solutions. The Riemann hypothesis is not merely a conjecture about the zeros of a single function but about the nature of these zeros in the context of analytic functions in general. By exploring harmonic conjugates, we are not abandoning the Riemann zeta function. Rather, we are generalizing its properties to a broader context that might hold the key to the proof. Conclusion: embracing broader horizons. Negating the claim that a proof must come solely from the Riemann zeta function itself, we argue for the legitimacy and potential of exploring related functions that act as harmonic conjugates. This approach does not dilute the proof but enhances it by providing a more robust and encompassing framework. The pursuit of mathematical truth often requires stepping beyond the immediate object of study to understand it within a wider context, one that, in this case, may very well include its harmonic conjugates. Clarification on the use of an alternate functional equation. In my proof of the Riemann hypothesis, the use of an alternate functional equation derived from the reflection properties of the zeta and gamma functions is a crucial element. This approach may raise questions, so it's important to clarify how and why this alternate functional equation is employed. 1. The role of functional equations in complex analysis. Functional equations are equations where the function itself is part of the equation, relating values of the function at different points. They are a powerful tool in complex analysis, often revealing deep symmetries and properties of functions. The classic example is the functional equation for the Riemann zeta function. This equation relates the values of the zeta function at s and 1 minus s, extending the function's behavior across the entire complex plane. 2. Derivation of the alternate functional equation. The alternate functional equation I propose is derived by carefully examining the reflection properties of both the zeta function and the gamma function. These reflection properties are well known in mathematics. By manipulating these properties, one can construct a new functional equation that is consistent with these reflections but provides a different perspective on the zeta function's behavior. This alternate equation is not arbitrary. It emerges naturally from the underlying properties of these functions. 3. Why use an alternate functional equation? The alternate functional equation serves several purposes. Extension of domain. It allows for the extension of the zeta function into regions where its traditional definition might be less informative or where different properties emerge. Unification with harmonic conjugates. This equation facilitates the identification of harmonic conjugates to the zeta function, leading to a broader framework where the zeta function and its variants can be unified. Insight into zeros and moduli. The equation helps reveal the distribution of zeros and the maximum and minimum moduli of the function in new, geometrically significant regions like the dual unit circle and the half-unit circle. 4. Ensuring consistency with the original zeta function. It's crucial to note that the alternate functional equation is not a replacement for the original one, but rather a complement to it. It maintains consistency with the Riemann zeta function's known properties while providing new insights that are not immediately apparent from the traditional approach. 5. Addressing concerns. Some may be concerned that introducing an alternate functional equation might deviate from the original problem's framework. However, mathematical exploration often involves such extensions to gain deeper insights or to apply known tools in novel ways. The alternate functional equation enriches the understanding of the zeta function without contradicting its established properties. Conclusion. The use of an alternate functional equation in my proof is a strategic and thoughtful approach that builds upon the established foundations of complex analysis. It allows for a richer exploration of the Riemann zeta function's properties and provides a pathway to address the Riemann hypothesis within a unified and comprehensive framework. This approach is both consistent with traditional mathematics and innovative in its exploration of new avenues. Clarification on the use of the delta function as a variant of the gamma function. In my proof of the Riemann hypothesis, the delta function plays a crucial role as a variant of the gamma function. This variant is derived from exploring the self-recurrence properties of the gamma function, leading to a deeper understanding of its relationship with the zeta function. The gamma function and its recurrence. The gamma function is a fundamental concept in mathematics, known for its self-recurrence properties. This self-recurrence means that the value of the gamma function at one point can be expressed in terms of its value at another, revealing a pattern of behavior that is key to many areas of analysis. Introducing the delta function. Building on the gamma function's self-recurrence, the delta function is introduced as a variant that captures some of the subtler aspects of this behavior. The delta function is specifically designed to interact with the zeta function in a way that complements and extends its properties. Why use the delta function? The delta function is integral to the proof for several reasons. Enhanced symmetry. It introduces additional symmetry to the mathematical framework, which is essential when seeking to connect the zeta function with its harmonic conjugates. Unification with harmonic conjugates. The delta function acts as a bridge, facilitating the unification of the zeta function with related functions that together provide a more complete picture. Support for the alternate functional equation. The delta function helps in the formulation of the alternate functional equation, which is central to extending the zeta function's behavior across a broader domain. Derivation and consistency. The delta function is not an arbitrary addition but is systematically derived from the gamma function's established properties. This ensures that the delta function is consistent with the mathematical principles underlying the gamma function, while also extending those principles in a way that is necessary for the proof. Addressing potential concerns. Introducing a new function in a proof involving well-known objects like the gamma function might raise concerns. However, the delta function is not a departure from the gamma function. Rather, it builds on and extends the gamma function's properties to meet the specific needs of this proof. Its introduction is necessary to address the complexities involved in the behavior of the zeta function under the alternate functional equation. Conclusion. The delta function is a carefully derived extension of the gamma function, designed to support the unification and extension of the zeta function in my proof of the Riemann hypothesis. It ensures that the zeta function and its variants are unified within a coherent framework, allowing the proof to address the hypothesis in a novel and mathematically sound way. Insight into the harmony of the proof and the harmonic conjugate theorem. The proof of the Riemann hypothesis that I've developed is deeply intertwined with the concepts of harmonic conjugates and the broader framework of complex analysis. This approach leverages the rich interplay between harmonic functions, the Cauchy-Riemann equations, and the harmonic conjugate theorem to bring together various elements into a coherent and harmonious whole. Background concepts. Laplace's equation and harmonic functions. Harmonic functions are solutions to Laplace's equation, a second-order partial differential equation. In two dimensions, if a function u, x, y satisfies Laplace's equation, i.e., the sum of its second partial derivatives with respect to each variable equals 0, it is called a harmonic function. Harmonic functions are central to many areas of mathematical physics and complex analysis due to their nice properties, such as being infinitely differentiable within their domain. Continuous differentiability and analytic functions. For a function to be harmonic, it must be continuously differentiable within its domain. In complex analysis, a function of a complex variable is said to be analytic or holomorphic if it is differentiable at every point in its domain. The real and imaginary parts of an analytic function are harmonic functions, which brings us to the concept of harmonic conjugates. The Cauchy-Riemann equations. The Cauchy-Riemann equations provide the necessary and sufficient conditions for a function to be analytic. These equations link the partial derivatives of the real and imaginary parts of a complex function. If a complex function satisfies the Cauchy-Riemann equations, it is not only analytic but also its real and imaginary parts are harmonic functions. The harmonic conjugate theorem. The harmonic conjugate theorem states that if u, x, y is a harmonic function, then there exists a function v, x, y such that the complex function f, z equals u, x, y plus 4x, y is analytic. The function v, x, y is called the harmonic conjugate of u, x, y. This theorem is fundamental because it shows how harmonic functions pair up to form analytic functions, which are the building blocks of much of complex analysis. How these concepts integrate in the proof. Unification through harmonic conjugates. In my proof, the Riemann zeta function and its variant, derived through an alternate functional equation, are viewed as harmonic conjugates. This approach builds directly on the harmonic conjugate theorem. By treating these functions as harmonic conjugates, we ensure that they form a unified analytic structure, consistent with the principles of complex analysis. Role of the delta function. The delta function, as a variant of the gamma function, is derived from the gamma function's self-recurrence properties. This function is designed to harmonize with the zeta function and its variants, ensuring that the entire framework satisfies the conditions of the harmonic conjugate theorem. This not only ties the functions together analytically but also ensures their behavior aligns with the broader principles of harmonic functions and their conjugates. Extending the zeta function's behavior. The alternate functional equation, supported by the delta function, extends the zeta function beyond its traditional domain. In doing so, it maintains the continuity and differentiability required by the Cauchy-Riemann equations, ensuring that the extended zeta function remains analytic. The maximum modulus principle, seen in the behavior of the function on the dual unit circle, and the distribution of zeros on the half-unit circle are direct consequences of this harmonic relationship. Complying with Liouville's theorem. Liouville's theorem asserts that a bounded entire function must be constant. In the context of my proof, the zeta function, after being unified and extended through harmonic conjugates, becomes an entire function that is unbounded but has well-defined behavior. This compliance with Liouville's theorem is a testament to the harmony of the functions within the analytic framework, further reinforcing the validity of the proof. Conclusion. The integration of these concepts, harmonic functions, the Cauchy-Riemann equations, harmonic conjugates, and analytic functions, creates a harmonious structure in the proof of the Riemann hypothesis. By ensuring that each component aligns with the principles of harmonic conjugates and complex analysis, the proof forms a coherent whole. This harmony not only adds mathematical elegance but also ensures that the proof is grounded in well-established theories, offering a fresh perspective on one of mathematics' most enduring challenges. The harmonic conjugate as an additive inverse of the zeta function. In the framework of my proof of the Riemann hypothesis, the harmonic conjugate of the Riemann zeta function plays a unique and critical role. Not only does it fit into the broader analytic structure, but it also acts as an additive inverse to the zeta function in certain contexts. This property adds an extra layer of depth to the proof and highlights the intricate relationships between these functions. Understanding the additive inverse. In mathematical terms, an additive inverse of a function f is another function g such that f plus g equals 0. In the context of complex analysis, if we say that a function v is an additive inverse of the Riemann zeta function zetas, it means that there are specific values or conditions where the sum of zetas and versus results in 0. Harmonic conjugate as an additive inverse. In the proof, the harmonic conjugate of the zeta function, derived through the reflection properties and involving the delta function, exhibits properties such that it negates the values of the zeta function under certain conditions. This means that for some values or regions in the complex plane, the sum of the zeta function and its harmonic conjugate results in 0. This additive relationship underscores a deeper connection between these functions and their harmonic properties. Implications of the additive inverse. 1. Enhanced symmetry. The property of the harmonic conjugate acting as an additive inverse adds symmetry to the framework. It implies that the zeta function and its conjugate are intricately linked, reinforcing the idea that they are part of a unified analytic structure. 2. Insight into zeros. The fact that the harmonic conjugate can negate the values of the zeta function in some cases provides additional insight into the distribution of zeros. Specifically, it suggests that the locations where this additive inverse relationship holds may be closely related to the zeros of the zeta function, offering a refined view of where and how these zeros are distributed. 3. Analytic continuation. The additive inverse property supports the analytic continuation of the zeta function by showing that its behavior can be balanced or countered in specific regions. This balancing act helps to ensure that the extended function remains analytic and adheres to the conditions required by the harmonic conjugate theorem. 4. Unification of functions. By demonstrating that the harmonic conjugate can act as an additive inverse, the proof shows that the zeta function and its conjugate are not merely related but are interdependent in a way that enriches our understanding of their joint behavior. Conclusion: the harmonic conjugate's role as an additive inverse of the Riemann zeta function adds a significant dimension to the proof. It highlights a deep and elegant symmetry between the zeta function and its conjugate, aligning with harmonic properties and contributing to the broader analytic framework. This relationship not only provides insights into the zeros of the zeta function but also supports the proof's coherence and validity within the context of complex analysis. Clarification on the behavior of the unified zeta function. In the context of my proof, after unifying the Riemann zeta function with its harmonic conjugate through the alternate functional equation, the function does not turn into zero but remains constant at a specific value. Here's a detailed explanation of this behavior. Unification and its effect. 1. Unification process. The unification of the Riemann zeta function with its harmonic conjugate involves extending the function using an alternate functional equation derived from the reflection properties of the zeta and gamma functions. This process creates a new framework where the zeta function and its conjugate work together to form a more comprehensive function. 2. Result of unification. Upon unification, the combined function is shown to be entire, meaning it is analytic and defined everywhere in the complex plane. This result stems from the fact that the harmonic conjugate complements the zeta function in such a way that the extended function remains well-behaved across the entire complex plane. Constant value at a zero. 1. Function value at a zero. After unification, the function does not approach zero but rather stabilizes at a constant value, denoted as a zero. This constant value is significant because it represents the value of the zeta function at a specific point, specifically zeta 1, which is 1. 2. Why it remains constant. The constancy at a zero is a result of the alternate functional equation. This equation ensures that, rather than the function approaching zero, it takes on a constant value. The alternate equation effectively balances the contributions from both the zeta function and its harmonic conjugate, leading to a stable and constant result. 3. Implications of a zero. The fact that the unified function remains constant at a zero, which is 1, the value of zeta 1, highlights that the harmonic conjugate has been correctly aligned to complement the zeta function, preserving a specific value rather than reducing to zero. This constancy underscores the harmony and stability achieved through the unification process. Conclusion. Post-unification, the combined function of the Riemann zeta function and its harmonic conjugate does not become zero but remains constant at a zero, which equals 1. This result is a direct consequence of the alternate functional equation used in the proof. The constancy of the function at this value signifies a successful integration of the zeta function with its harmonic conjugate, ensuring the function is entire and well-behaved across the complex plane. Laurent expansion and radius of convergence. When dealing with the Riemann zeta function and its simple pole at s equals 1, the Laurent expansion helps us understand the behavior of the function near this point and its radius of convergence. Laurent expansion. 1. Definition. The Laurent expansion of a function around a singular point, such as a pole, includes both positive and negative powers of the variable. For the Riemann zeta function near s equals 1, the expansion includes a term that behaves like 1/s-1, representing the pole along with other terms that are regular and analytic at s equals 1. 2. Radius of convergence. The radius of convergence for this series is defined by the distance to the nearest singularity. In the case of the zeta function, this radius is limited by the singularity at s equals 1, meaning the series converges in a region around s equals 1 but does not include s equals 1 itself. Impact of removing the simple pole. 1. Modification through unification. In my proof, the zeta function is unified with its harmonic conjugate to cancel out the pole at s equals 1. This process removes the term 1/s-1 from the Laurent expansion, leaving a series that is analytic at s equals 1. Even if someone wants to continue with the Laurent expansion, he or she has to approach the unification from the coefficient of the first term, which should be 1 again. 2. New radius of convergence. After the pole is removed, the Laurent series around s equals 1 transforms into a Taylor series, which only includes non-negative powers of s-1. This change extends the radius of convergence to cover the entire complex plane, resulting in a function that is entire, meaning it is analytic everywhere. Conclusion. The Laurent expansion of the Riemann zeta function near S equals 1 initially includes a term for the simple pole and regular terms, with its radius of convergence restricted by this singularity. By removing the pole through unification with its harmonic conjugate, the function's expansion becomes a normal Taylor series expansion involving eta function or alternate zeta function, expanding its radius of convergence to the whole complex plane and ensuring that the function is entire, clarifying the redefinition of trivial zeros with the harmonic conjugate. In the context of my proof of the Riemann hypothesis, the role of the harmonic conjugate extends to redefining the trivial zeros of the Riemann zeta function. Here's an explanation of how this redefinition occurs and its implications. Understanding trivial zeros. 1. Definition: the trivial zeros of the Riemann zeta function are the zeros that occur at negative even integers, specifically at s equals -2, -4, -6, and so on. These are well known and arise due to the functional equation of the zeta function. 2. Functional equation. The Riemann zeta function satisfies a functional equation that relates zetas to zeta, 1 minus s. This equation implies that the zeta function has zeros at these negative even integers. Redefining trivial zeros with harmonic conjugate. 1. Role of the harmonic conjugate. In my proof, the harmonic conjugate of the zeta function, derived through the alternate functional equation, plays a crucial role in redefining how zeros are represented. By integrating the harmonic conjugate, the combined function has new properties that alter the conventional understanding of trivial zeros. 2. New perspective on zeros. The harmonic conjugate helps transform the zeta function into a form where the behavior of zeros is influenced by both the zeta function and its conjugate. The trivial zeros, which were traditionally seen as intrinsic to the zeta function alone, are now redefined within this unified framework. 3. Impact on the zeta function. With the inclusion of the harmonic conjugate, the zeros of the combined function take on new characteristics. The trivial zeros are effectively absorbed or modified in this unified function, reflecting a more comprehensive view of where and how zeros occur. Implications of the redefinition. 1. Enhanced understanding. The redefinition provides a deeper understanding of the distribution of zeros by showing how the harmonic conjugate affects the zeta function's behavior. This approach integrates the zeros into a broader analytical framework. 2. Analytic continuation. By redefining the trivial zeros, the proof emphasizes the function's analytic continuation and how the zeros fit into the larger structure of the function, reinforcing the entire function's properties. 3. Harmonization with hypothesis. This redefinition supports the proof of the Riemann hypothesis by showing that the zeros of the zeta function, including the trivial ones, are consistently represented within the unified framework, aligning with the broader hypothesis about the location of non-trivial zeros. Conclusion. In my proof, the trivial zeros of the Riemann zeta function are redefined through the harmonic conjugate, offering a new perspective on their behavior. The harmonic conjugate integrates into the function's framework, modifying the traditional view of these zeros and enhancing our understanding of their distribution in relation to the unified function. Clarifying the unified zeta function's nature, not injective and not surjective. In the context of the unified Riemann zeta function, it is important to understand its properties in terms of injectivity and surjectivity. Here's a clear explanation. Nature of the unified zeta function. 1. Injectivity. A function is injective if different inputs always map to different outputs. The unified zeta function continues to be non-injective. This means that there are still multiple distinct inputs that can produce the same output value. In other words, different points in the domain of the unified zeta function can lead to the same value in its range. 2. Surjectivity. A function is surjective if every possible output value in the codomain is achieved by some input from the domain. Despite the unification, the unified zeta function remains non-surjective. This means that there are values in the codomain that are not covered by the function. In other words, not every possible output value is obtainable from some input value in the complex plane. Impact of unification on function properties. 1. Preservation of non-injectivity. The unification process, while addressing issues related to poles and zeros and providing a more comprehensive analytic structure, does not resolve the issue of injectivity. The function remains non-injective, reflecting that multiple distinct inputs can still map to the same output. 2. Preservation of non-surjectivity. Similarly, the unification process does not make the function surjective. There are still values in the range that the unified zeta function cannot achieve. This limitation indicates that the function does not cover its entire codomain. Implications. 1. Analytic behavior. The fact that the unified zeta function remains both non-injective and non-surjective highlights the inherent complexity of the function's behavior. It illustrates that while the function has been extended and modified, it does not achieve these ideal properties. 2. Fit with the hypothesis. The non-surjectivity of the unified zeta function is a feature that needs to be considered in the context of the Riemann hypothesis. It suggests that the function's behavior, including the distribution of zeros, is still constrained by its fundamental properties, even after unification. Conclusion. The unified Riemann zeta function continues to be neither injective nor surjective. While the unification process has modified and extended the function, it does not achieve injectivity. Distinct inputs may map to the same output or surjectivity. Not all possible output values are covered. Understanding these characteristics is crucial for analyzing the function's role in the proof of the Riemann hypothesis and its overall analytic properties. As promised in my last video today, we shall explore a revolutionary concept: the integration of complex numbers with the decimal number system. This idea promises to enhance our understanding of mathematics and extend its applications. Let's dive into the history, basic concepts, attempts at integration, and my unique approach to this intriguing endeavor, which includes a modified place value system and novel decimal operations. To appreciate the integration of complex numbers with the decimal system, we must first understand their origins. The decimal number system, also known as the base 10 system, dates back to ancient civilizations like the Egyptians and the Babylonians. It was formalized by Indian mathematicians and spread to the Western world through the works of Islamic scholars. On the other hand, complex numbers have a more tumultuous history. The notion of imaginary numbers emerged in the 16th century when mathematicians like Cardano grappled with solutions to cubic equations that involved the square root of negative numbers. The formal acceptance and development of complex numbers came later, with significant contributions from Euler, Gauss, and others in the 18th and 19th centuries. The decimal number system is a positional numeral system that uses 10 digits, from 0 to 9. Each digit's position represents a power of 10, allowing for the representation of both whole numbers and fractional numbers. Complex numbers, on the other hand, consist of a real part and an imaginary part. This extension of the real numbers allows for the solution of equations that have no real solutions. This concept might seem abstract, but it has practical applications in fields like engineering, physics, and computer science. Historically, the integration of complex numbers into the decimal system hasn't been a mainstream focus. However, there have been efforts to unify different complex number systems under broader mathematical frameworks. For example, hypercomplex numbers, including quaternions and octonions, extend complex numbers to higher dimensions. These efforts demonstrate the potential for a unified numerical system. I don't know why complex numbers and the decimal system have remained separate entities. Being an Indian guy from the East where decimal system took birth, I propose a possible integration thereof with the complex numbers from the West. The challenge is to find a way to integrate these systems seamlessly. Imagine if we could extend the familiar and intuitive decimal system to include complex numbers, providing a unified framework that simplifies calculations and broadens our mathematical toolkit. Allow me to present my approach towards integrating complex numbers with the decimal number system. This vision involves a modified place value system and novel rules for decimal operations to seamlessly incorporate complex numbers. In this framework, the first imaginary part has a place value of 100, and every subsequent imaginary part increases by 10 times its predecessor. Thus, the place values for the imaginary parts are 100, 1000, 10,000, and so on. This system preserves the hierarchical structure of the decimal system while extending it to accommodate complex numbers. we introduce a unique rule for operations involving the signs of imaginary parts. If the imaginary part has a positive sign, it multiplies the real part. Conversely, if the imaginary part has a negative sign, it divides the real part. This rule integrates the effects of the imaginary components into the real number operations in a consistent and logical manner. In this system, imaginary numbers are replaced by starting with the natural logarithm of 2 and its successive logarithms. This substitution grounds the imaginary parts in well-known mathematical constants, providing a bridge between real and complex numbers. The problematic point will be negative logarithm of -1, which also can be fixed or replaced by double of the natural logarithm of 2 following the definition of imaginary number iota. This approach is consistent with the principles of the decimal system and the properties of complex numbers. By integrating complex numbers in this way, we create a seamless transition from real to complex numbers. Furthermore, this framework can unify hypercomplex numbers, such as quaternions and octonions, by extending the positional system into higher dimensions. Each dimension could represent a different component of these hypercomplex numbers, preserving the structural integrity of the decimal system while accommodating greater complexity. Integrating complex numbers with the decimal number system through a modified place value system and my novel rules for decimal operations is a practical and innovative step towards unifying various numerical systems. By viewing complex numbers as an extended decimal system with unique place values and operational rules, we preserve consistency and open the door to unifying more complex number systems. This vision holds the promise of a more cohesive and comprehensive mathematical framework, enhancing our understanding and application of numbers in diverse fields. Thank you for your attention, and I hope this exploration has sparked your curiosity and appreciation for the innovative possibilities in the world of mathematics. As with any groundbreaking idea, the integration of complex numbers with the decimal number system is bound to face scrutiny and criticism. This is a natural part of the process of advancing knowledge and pushing the boundaries of what we understand. Let me address some of the probable criticisms and defend my propositions with clarity and conviction. One of the primary criticisms may be that this new system is too complex and impractical for everyday use. Critics might argue that the modified place value system and new rules for operations add unnecessary layers of complication. While the proposed system introduces new concepts, it builds on the familiar structure of the decimal system. The place value modification and the rule of signs are designed to maintain consistency and logic within the system. The use of natural logarithms provides a mathematically rigorous foundation that can unify real and complex numbers. In practical terms, the adoption of this system can be incremental, starting in advanced fields like theoretical mathematics, physics, and engineering, where the benefits of a unified numerical framework are most pronounced. Another criticism might come from a purist mathematical perspective, arguing that such a system disrupts the elegance and simplicity of existing mathematical structures. Mathematics has a history of evolving to incorporate new ideas that initially seemed counterintuitive or complex. The acceptance of zero, negative numbers, and even complex numbers themselves were met with resistance. Yet, these concepts have become fundamental to modern mathematics. My approach is not to replace existing systems, but to extend them, providing a new perspective that enriches our understanding and opens up new possibilities for exploration and application. As we delve into the integration of complex numbers with the decimal number system, one aspect of my proposal is likely to attract significant criticism: the replacement of the imaginary unit with the natural logarithm of 2 and its successive logarithms. Let me address and defend this part of my proposition in detail. Critics might argue that replacing the imaginary unit with natural logarithm of 2 and its successive logarithms undermines the mathematical legitimacy and rigor of complex numbers, as the imaginary unit iota has a well-defined and fundamental property. While the imaginary unit iota is indeed fundamental in traditional complex number theory, my proposal aims to reinterpret the imaginary component in a way that is consistent with logarithmic growth. The use of natural logarithm of 2 and its successive logarithms grounds the imaginary part in well-known mathematical constants that also exhibit a clear, hierarchical relationship. This transformation does not negate the properties of iota, but rather provides a new framework that could offer deeper insights, especially in fields that already make extensive use of logarithmic functions, such as information theory and signal processing. Another criticism may focus on the conceptual clarity and intuition of replacing iota with logarithms, arguing that this substitution could confuse rather than clarify the understanding of complex numbers. The integration of natural logarithms into the imaginary component introduces a new layer of conceptual clarity by linking complex numbers directly to exponential and logarithmic growth, which are pervasive in nature and various scientific disciplines. For instance, exponential growth is fundamental in fields ranging from population dynamics to finance. By expressing the imaginary part in terms of logarithms, we provide a bridge to these applications, making the abstract concept of iota more tangible and relevant. Furthermore, as students and practitioners become accustomed to this new framework, the initial confusion will give way to a deeper, more intuitive grasp of complex relationships. Critics might be concerned about the impact this change will have on existing theorems, applications, and computations that rely on the traditional definition of iota. My approach is not intended to replace the existing framework, but to provide an alternative perspective that can coexist with traditional complex number theory. Existing theorems and applications remain valid within their established contexts. However, in areas where logarithmic relationships are more prevalent, this new framework could offer enhanced computational and conceptual tools. Over time, mathematicians and scientists may develop new theorems and applications that leverage this reinterpretation, leading to novel insights and advancements. Educators might express concern about the difficulty of teaching this new system, especially when students are already grappling with traditional concepts. Education is about preparing students to think critically and adapt to new ideas. Introducing this system can be seen as an opportunity to deepen students' understanding of mathematical concepts and their interrelations. By gradually integrating these ideas into advanced mathematics curricula, we can provide students with a more comprehensive toolkit that will serve them well in various scientific and engineering disciplines. Established fields that rely on current mathematical systems, such as engineering, physics, computing, and advanced technologies, might resist adopting a new numerical framework. Innovation often encounters resistance, but it also drives progress. The proposed system's primary applications lie in advanced theoretical work and cutting-edge technologies. Over time, as the benefits become evident, more fields may adopt the new framework. Additionally, this system does not mandate an immediate overhaul of existing practices. It can coexist with current systems, offering an alternative approach where beneficial. In any paradigm shift, there may be skepticism aimed at the proponents of the new idea. Critics might question the credibility or motivations behind such a proposal. Throughout history, many pioneers in science and mathematics have faced personal attacks and skepticism. It is crucial to stay focused on the merits of the idea and the potential it holds for advancing our understanding. My motivations are rooted in a genuine desire to explore new frontiers in mathematics and to contribute to the body of knowledge in a meaningful way. Constructive criticism is welcome, as it helps refine and improve the proposition. However, personal attacks will not deter the pursuit of progress. Defending the integration of complex numbers with the decimal number system requires a steadfast belief in the value of innovation and an open-minded approach to criticism. By addressing concerns thoughtfully and demonstrating the potential benefits of this new framework, we can foster a productive dialogue that ultimately advances our understanding and application of mathematics. Change is challenging, but it is also necessary for growth and discovery. The integration of complex numbers with the decimal number system through a modified place value system and novel operational rules is a practical and innovative step towards unifying various numerical systems. By viewing complex numbers as an extended decimal system with unique place values and logarithmic replacements, we preserve consistency and open the door to unifying more complex number systems. This vision holds the promise of a more cohesive and comprehensive mathematical framework, enhancing our understanding and application of numbers in diverse fields. Thank you for your attention, and I look forward to engaging in further discussions and explorations of this exciting concept. As we stand on the brink of unprecedented technological advancements, the integration of complex numbers with the decimal number system opens up a myriad of possibilities. This novel concept can significantly impact two of the most transformative fields of our time: quantum computing and artificial intelligence, AI. By merging these mathematical frameworks, we can push the boundaries of what is possible, enhancing computational efficiency, accuracy, and capabilities. Quantum computing operates on the principles of quantum mechanics, harnessing the unique properties of quantum bits, qubits, that can exist in multiple states simultaneously. This characteristic, known as superposition, along with entanglement, allows quantum computers to perform complex calculations at speeds unattainable by classical computers. Traditionally, quantum states are represented using complex numbers. By integrating these complex numbers into the decimal system, we can develop a more unified and intuitive framework for representing quantum states. This could simplify the mathematical models used in quantum algorithms, making them more accessible and easier to understand. Quantum error correction is a critical challenge in the development of reliable quantum computers. The novel system of representing complex numbers with a modified place-value system and natural logarithms could lead to more robust error-correcting codes. These codes would leverage the hierarchical and logarithmic structure to detect and correct errors more efficiently, enhancing the stability and reliability of quantum computations. Quantum algorithms, such as Shor's algorithm for factoring large numbers and Grover's algorithm for searching unsorted databases, rely heavily on complex number computations. By integrating complex numbers with the decimal system, we can streamline these algorithms, potentially leading to faster and more efficient computations. This integration could also facilitate the development of new quantum algorithms that leverage the unique properties of the simplex number system. Artificial intelligence, particularly in areas like machine learning and neural networks, relies on complex mathematical operations to process and analyze vast amounts of data. The integration of complex numbers with the decimal system can enhance these operations in several ways. Neural networks often use complex numbers to model certain types of data and relationships. By adopting the integrated complex decimal system, we can develop more advanced neural network architectures that are capable of handling complex data more efficiently. This could lead to improvements in tasks such as image recognition, natural language processing, and predictive analytics. The hierarchical and logarithmic structure of the integrated system allows for a more nuanced representation of data. This can improve the way AI models interpret and process information, leading to more accurate predictions and insights. For instance, in the realm of deep learning, this system could enhance the way features are extracted and weighted, resulting in more robust models. Machine learning algorithms, such as gradient descent, rely on complex number calculations to optimize model parameters. The new framework can simplify these calculations, making the optimization process more efficient. This could lead to faster training times and more accurate models, accelerating the development and deployment of AI technologies. One of the most exciting possibilities is the creation of a unified mathematical framework that seamlessly integrates AI and quantum computing. By leveraging the integrated complex decimal system, we can develop hybrid quantum classical algorithms that combine the strengths of both paradigms. This could lead to breakthroughs in fields like quantum machine learning, where quantum computers enhance the capabilities of classical AI models. The integration of complex numbers with the decimal number system represents a bold and innovative step towards advancing quantum computing and artificial intelligence. By providing a more intuitive, robust, and efficient mathematical framework, this novel concept has the potential to unlock new possibilities and drive transformative advancements in these fields. As we continue to explore and refine this integration, we can look forward to a future where the boundaries of computation and intelligence are continually expanded, leading to a deeper understanding of the universe and more powerful technological tools. Thank you for your attention, and I look forward to engaging in further discussions on the exciting potential of this groundbreaking idea. The integration of complex numbers with the decimal number system offers a revolutionary framework that can transform various fields, including human disease drug development, genetic modification, and cancer treatment. By merging these mathematical systems, we can enhance computational models, improve data analysis, and develop innovative approaches to tackle some of the most challenging problems in medicine and biotechnology. The process of drug development is intricate and time-consuming, requiring precise modeling and analysis of biological systems and molecular interactions. The integrated complex decimal system can significantly impact this field in several ways. Computational models used in pharmacology often rely on complex numbers to simulate the behavior of drugs within the human body. By integrating complex numbers with the decimal system, we can develop more accurate and efficient models. This can improve the prediction of drug behavior, including absorption, distribution, metabolism, and excretion, ADME, leading to faster and more reliable drug development processes. Molecular dynamic simulations are essential for understanding the interactions between drugs and their target proteins. The novel framework can simplify these simulations by providing a more intuitive representation of molecular interactions. This can enhance our ability to identify potential drug candidates and optimize their efficacy and safety. The hierarchical and logarithmic structure of the integrated system allows for more efficient data analysis and pattern recognition. This can expedite the identification of promising drug compounds from large datasets, reducing the time and cost associated with drug discovery. Genetic modification involves altering the genetic material of organisms to achieve desired traits. The integration of complex numbers with the decimal system can advance this field by improving the precision and efficiency of genetic engineering techniques. Gene editing technologies, such as CRISPR-Cas9, rely on precise targeting and modification of specific DNA sequences. The new mathematical framework can enhance the algorithms used to design and optimize guide RNAs, increasing the accuracy and efficiency of gene editing. Genetic modification requires the analysis of vast amounts of genomic data. The integrated system can streamline this analysis, allowing researchers to identify genetic variations and their functional impacts more efficiently. This can accelerate the development of genetically modified organisms with desired traits, such as disease resistance or improved nutritional content. Synthetic biology involves designing and constructing new biological parts and systems. The complex decimal integration can provide a more robust foundation for modeling and simulating synthetic biological systems, leading to more reliable and scalable synthetic biology applications. Cancer treatment is a multifaceted challenge that requires precise targeting of cancer cells while minimizing damage to healthy tissues. The novel mathematical framework can significantly contribute to the development of more effective and personalized cancer therapies. The integration of complex numbers with the decimal number system holds the potential to revolutionize human disease drug development, genetic modification, and cancer treatment. By providing a more intuitive, robust, and efficient mathematical framework, this novel concept can enhance computational models, improve data analysis, and lead to innovative approaches in medicine and biotechnology. As we continue to explore and refine this integration, we can look forward to groundbreaking advancements that improve human health and well-being. Thank you for your attention, and I am excited to engage in further discussions on the transformative potential of this groundbreaking idea. The integration of complex numbers with the decimal number system, hereby termed the simplex number system, represents a revolutionary framework that can significantly advance various fields. In information technology and telecommunication, this novel system can enhance computational efficiency, data representation, signal processing, and encryption, among other areas. Let's explore the potential applications of the simplex number system in these fields. Data storage and compression are critical for managing the vast amounts of information generated daily. The simplex number system can provide a more efficient representation of complex data, reducing storage requirements and improving compression algorithms. By leveraging the hierarchical structure and logarithmic relationships, we can develop more advanced data compression techniques that preserve data integrity while minimizing storage space. Many algorithms in computer science, such as those used in graphics processing, machine learning, and numerical analysis, involve complex number calculations. The simplex number system can streamline these computations, leading to faster and more efficient algorithms. This improvement can enhance the performance of various applications, from rendering high-quality graphics to training deep learning models. Cryptographic algorithms rely on complex mathematical operations to secure data. The simplex number system can introduce new methods for encryption and decryption, leveraging the unique properties of the integrated complex decimal framework. This can enhance the security of digital communications and transactions, making it more difficult for malicious actors to breach cryptographic defenses. Error detection and correction are essential for maintaining data integrity in digital systems. The simplex number system can improve the design of error-correcting codes, such as Reed-Solomon and LDPC codes, by providing a more robust mathematical foundation. This can enhance the reliability of data transmission and storage, reducing the likelihood of data corruption and loss. Signal processing is at the heart of telecommunication, involving the manipulation and analysis of signals to transmit information. The simplex number system can enhance digital signal processing, DSP, algorithms by providing a more intuitive representation of complex signals. This can lead to more efficient filtering, modulation, and demodulation techniques, improving the quality and reliability of communication systems. Channel coding techniques, such as error-correcting codes, are crucial for maintaining the integrity of transmitted data. The hierarchical and logarithmic structure of the simplex number system can improve the design of these codes, making them more efficient at detecting and correcting errors. This can enhance the performance of communication channels, particularly in noisy environments. Modulation schemes such as quadrature amplitude modulation, QAM, and phase shift keying, PSK, rely on complex number operations to encode data onto carrier waves. The simplex number system can introduce new modulation techniques that leverage its unique properties, potentially increasing the data throughput and robustness of communication systems. Telecommunication networks rely on complex algorithms to manage data traffic, allocate resources, and optimize performance. The simplex number system can enhance these algorithms, leading to more efficient network management and improved quality of service, QoS. This can result in faster data transfer rates, reduced latency, and better overall network performance. Multiple input, multiple output, MIMO, and orthogonal frequency division multiplexing, OFDM, are key technologies in modern wireless communication systems, including 4G and 5G networks. These technologies rely on complex number operations for signal processing and channel estimation. The simplex number system can optimize these processes, improving the performance and capacity of wireless networks. The simplex number system offers a transformative approach to handling complex numbers, providing a more intuitive, robust, and efficient mathematical framework. In the fields of information technology and telecommunication, this system can significantly enhance data storage, computational algorithms, cryptography, signal processing, channel coding, modulation schemes, and network optimization. By adopting the simplex number system, we can unlock new possibilities and drive advancements that will shape the future of digital communication and technology. Thank you for your attention, and I look forward to exploring the transformative potential of the simplex number system with you. The integration of complex numbers with the decimal number system, termed the simplex number system, provides a transformative mathematical framework. This system can significantly impact weather forecasting and climate control by enhancing data analysis, modeling, and prediction capabilities. Let's explore the potential applications of the simplex number system in these critical fields. Numerical weather prediction models rely on complex mathematical equations to simulate atmospheric conditions. The simplex number system can streamline these equations, making computations more efficient and accurate. This can lead to improved short-term and long-term weather forecasts, providing more reliable information for disaster preparedness and resource management. Data assimilation involves integrating observational data into weather models to improve their accuracy. The hierarchical and logarithmic structure of the simplex number system can enhance data assimilation techniques by providing a more precise representation of complex datasets. This can result in better initial conditions for weather models, leading to more accurate predictions. Climate models simulate the long-term behavior of the Earth's climate system. By incorporating the simplex number system, these models can better capture the intricate interactions between the atmosphere, oceans, and land surfaces. This can improve our understanding of climate change and its impacts, aiding in the development of effective mitigation and adaptation strategies. Remote sensing technologies, such as satellites and radar, generate vast amounts of data that need to be processed and analyzed. The simplex number system can optimize these processes, enabling more efficient extraction of meaningful information from raw data. This can enhance the accuracy and timeliness of weather forecasts and climate monitoring. Geoengineering involves deliberate interventions in the Earth's climate system to mitigate the effects of climate change. The simplex number system can provide more accurate and reliable models for evaluating the potential impacts of geoengineering techniques, such as solar radiation management and carbon dioxide removal. This can inform decision-making and policy development in this controversial field. Effective climate control requires continuous monitoring of environmental variables, such as greenhouse gas concentrations, temperature, and humidity. The simplex number system can improve the analysis of environmental data, providing more detailed and accurate information on the state of the climate. This can support efforts to manage and control climate-related phenomena. Long-term climate predictions are essential for understanding future climate scenarios and planning mitigation strategies. The simplex number system can enhance the performance of climate prediction models by providing a more robust mathematical foundation. This can lead to more reliable projections of climate change impacts, supporting global efforts to address this critical issue. Effective climate control requires optimal management of natural resources, such as water and energy. The simplex number system can enhance resource management algorithms by providing more accurate and efficient models. This can support sustainable practices and improve resilience to climate-related challenges, such as droughts and extreme weather events. The simplex number system offers a revolutionary approach to handling complex numbers, providing a more intuitive, robust, and efficient mathematical framework. In the fields of weather forecasting and climate control, this system can significantly enhance data analysis, numerical weather prediction, climate modeling, remote sensing data processing, geoengineering models, environmental monitoring, climate prediction models, and resource management. By adopting the simplex number system, we can unlock new possibilities and drive advancements that will improve our ability to predict, monitor, and manage the impacts of weather and climate. Thank you for your attention, and I look forward to exploring the transformative potential of the simplex number system with you. A Type 2 civilization, according to the Kardashev scale, is a society that has harnessed the full energy potential of its star. Achieving this level of advancement requires groundbreaking technological innovations, efficient energy management, and robust infrastructure. The integration of complex numbers with the decimal system, termed the simplex number system, can play a pivotal role in this journey. Here, we explore how the simplex number system can contribute to humanity's progression towards becoming a Type 2 civilization. The construction of a Dyson sphere, a hypothetical megastructure that encompasses a star to capture its energy, requires advanced engineering and precise calculations. The simplex number system can streamline the complex computations involved in designing and constructing such structures. By enhancing the accuracy and efficiency of these models, we can optimize the materials and techniques used, making the concept of harvesting stellar energy more feasible. Storing the immense energy harvested from a star demands advanced energy storage solutions. The simplex number system can improve the design and efficiency of these storage systems by providing more accurate models for energy conversion and storage dynamics. This can lead to the development of high-capacity, durable energy storage technologies that can sustain a Type 2 civilization's energy needs. Accurate navigation through space is crucial for interstellar travel and colonization. The simplex number system can enhance astrodynamics models, making it easier to calculate trajectories, optimize fuel usage, and predict gravitational influences. This can improve the safety and efficiency of long-duration space missions, facilitating the exploration and colonization of other star systems. Terraforming, the process of modifying a planet's environment to make it habitable, requires precise control over various environmental factors. The simplex number system can enhance the models used for simulating atmospheric, geological, and hydrological processes. This can lead to more effective strategies for transforming hostile planetary environments into habitable ones, paving the way for human colonies beyond Earth. Quantum computing is essential for processing the vast amounts of data and solving the complex problems associated with a Type 2 civilization. The simplex number system can optimize quantum algorithms and error correction techniques, enhancing the performance and reliability of quantum computers. This can accelerate technological advancements and enable new breakthroughs in various scientific fields. AI plays a critical role in managing the sophisticated infrastructure and technologies of a Type 2 civilization. By improving the efficiency of AI algorithms and data analysis techniques, the simplex number system can enhance the capabilities of AI systems. This can lead to more intelligent and autonomous systems for managing resources, conducting scientific research, and ensuring societal stability. Effective communication across vast interstellar distances requires advanced signal processing and data transmission techniques. The simplex number system can optimize these processes, making it possible to maintain high bandwidth, low-latency communication networks between distant star systems. This can ensure seamless information exchange and coordination among different parts of a Type 2 civilization. Managing the massive amounts of data generated by a Type 2 civilization necessitates efficient data processing and analysis. The simplex number system can enhance data compression, storage, and retrieval techniques, making it easier to handle and interpret large datasets. This can improve decision-making processes and support the continuous advancement of technology and knowledge. Efficient utilization of planetary resources is crucial for sustaining a Type 2 civilization. The simplex number system can improve models for resource extraction, processing, and distribution, ensuring optimal use of available materials. This can reduce waste, minimize environmental impact, and support sustainable development practices. Maintaining the balance of biospheres on multiple planets requires sophisticated ecological models. The simplex number system can enhance our understanding of complex ecological interactions, leading to better management of planetary ecosystems. This can ensure the long-term sustainability and health of habitats within a Type 2 civilization. The simplex number system offers a transformative approach to handling complex mathematical problems, providing a more intuitive, robust, and efficient framework. In the quest to become a Type 2 civilization, this system can significantly enhance energy management, space exploration, advanced technologies, communication networks, and sustainable resource management. By adopting the simplex number system, humanity can unlock new possibilities and drive the advancements necessary to achieve a Type 2 civilization, harnessing the full energy potential of our star and ensuring our long-term survival and prosperity.